If you're getting into Python, you've probably hit a couple of big walls pretty fast. First, just figuring out what your data is, and second, what to do when your beautiful code just, well, breaks. So that's what we're going to tackle, turning that frustration into some real know-how.
Oh, we've all been there. You know the feeling, right? You write a few lines of code, you hit run, and instead of magic, you just get a wall of angry red text. It's so frustrating. But what if I told you that red text isn't a stop sign? It's more like a treasure map.
And that right there is the big mindset shift we need to make. See, every error message is actually a clue. It tells you where to look and what might have gone wrong. So let's start building your detective toolkit, beginning with the absolute basics, the evidence itself. Okay, so before we can build anything cool, we have to understand our materials. And in Python, the most fundamental materials we have are called data types. You can think of them like the bricks, the wood, and the glass you'd use to construct a building.
So what is a data type, really? It's basically just a label that tells Python what kind of information a variable is holding onto. Is it a number? Is it some text? Is it a whole collection of things? Knowing the type is absolutely crucial because, you can't do math with a sentence and you can't capitalize a number.
The cool thing is Python gives you a bunch of these materials right out of the box. We're going to focus on the three you'll be using all the time. Numbers for all your math, strings for handling any kind of text, and lists for keeping your data organized in collections. First up, numbers. This one's pretty straightforward. Python usually breaks them down into three types. You've got your integers, which are just plain old whole numbers. Then you have floating point numbers, or floats, which are just numbers with a decimal point. And yeah, for all you math and science wizards out there, it even supports complex numbers. Next up, we've got strings. Anytime you see text in your code, it's a string. It's really just a sequence of characters. One of the neat things about Python is you can use either single quotes or double quotes to create them, which is actually super handy and gives you a bit of flexibility. And the last one for now is the list. The best way to think about a list is like a shopping cart. It's an ordered collection, which means the items stay in the exact sequence you put them in, and they are incredibly versatile. A single list can hold numbers, strings, and even other lists, all at the same time. All right, this next part is super important. It's kind of like a secret rule in Python that explains so much about how it works. It's the difference between data that can be changed and data that can't. We call this concept mutability. Okay, so here's the breakdown. Mutable just means changeable. A list is the perfect example. You can add stuff, remove stuff, or change items after you've made it. But immutable means unchangeable. Once you create a string or a number, you can't actually alter that original piece of data. This is a huge deal for writing efficient code and avoiding some really strange bugs. Now, if you're thinking, how can I prove this? Well, Python has a cool little function for that called ID. It shows you the unique memory address for any piece of data. Think of it like a specific parking spot in the computer's memory. So look here. When we set x to 10, it gets a parking spot. But notice when we set x to 20. We don't change the 10. Instead, Python creates a brand new number 20 and a completely different parking spot and just points the name x to this new spot. So here's what that looks like in real code. On the left, we have a list made with square brackets. We can go in and change that first item from 6 to 55, no problem. It works. But on the right, we have a tuple, which uses parentheses. Because it's immutable, when we try to do the exact same thing, Python just says nope and throws an error. It literally cannot change the contents of that tuple. Okay, so we know our different materials. But what if we need to change one type into another? Like turning a number into text. In Python, we call that process type conversion. Now, sometimes Python is pretty smart and will do this for you automatically. We call that implicit conversion. But most of the time, we have to be the ones to tell Python exactly what we want. This is called explicit conversion, and it's a skill you're going to use all the time. And here's a classic example of why this is so important. In the first line, the variable a is holding the string 101. See the quotes? That means it's text, not a number you can do math with. If you tried to add 10 to it, your code would crash. So you have to explicitly convert it using the int function. Now the new variable b holds the actual integer 101, and you can do math with it all day long. All right, let's switch gears. We know our materials. We know how to shape them. But what happens when it all comes crashing down? It's time to dissect the anatomy of an error. When it comes to bugs, they pretty much fall into one of three big categories. You've got syntax errors, which are like typos, runtime errors, which happen while the program's actually running, and then there are logical errors. These are the sneaky ones, where the program runs, but it just does the wrong thing. First up, you've got syntax errors.
Honestly, these are the easiest ones. You've just broken a grammar rule of the Python language. Maybe you forgot a colon or a closing parentheses. It's just a typo, and the good news is Python is usually really good at pointing you to the exact line where you messed up.
Next are runtime errors. Now these are a little different. Your grammar is perfect, your syntax is fine, but you've told the computer to do something that's just impossible. The classic example is trying to divide a number by 0. Your code is totally valid right up until the moment it tries that impossible task, and then it just crashes.
And finally, we get to the sneakiest, most frustrating bug of all, the logical error. With these, the program runs perfectly. No crashes, no red text. But the final answer is just plain wrong. It's like building a calculator that tells you 2 + 2 = 5. The code is running, but it's not doing what you actually wanted it to. These are the ones that require some real detective work.
So, okay, how on earth do we hunt down those logical errors and find the clues hidden in our code? Well, it's time to put on our detective hats and learn the most fundamental debugging technique there is. And believe it or not, your first, best, and most powerful tool is something super simple, the print statement. This is used by total beginners and senior engineers alike. If your calculation is coming out wrong, just start printing the values of your variables at every single step. By watching how they change, you can pinpoint the exact moment your logic goes off the rails.
Now here's a little pro tip to make your print debugging way cleaner and easier to read. Instead of just printing raw variables, use the .format method. This lets you write out a nice descriptive message, and then you can just drop your variable values right into those curly braces. It makes your output so much easier to understand, especially when you're trying to track a bunch of different variables at once.
So there you have it. We've looked at the basic building blocks of data, the different types of errors, and now you know that an error isn't a dead end, it's a clue. You've got your first and most important tool, the print statement, to start your investigation. The only question left is, what mystery are you going to solve first?